All right, may I have your attention? So let's take a look at the quiz and try to answer it. Really, you just had to read properly the equation. And, well, I wanted to be specific about details. So whenever we speak about current is always across a surface. So current, or through a surface. So current through a surface is equal to the flux of current density over the same surface. Right. Now, so when we calculate flux, let's say that current, let's say that we have a certain surface. We are interested in the current flowing through this surface. When we calculate flux, we have to divide the surface into tiny pieces. For each piece, we have to calculate scalar product. Now remember that we know 4 products, 4 different multiplications, because I noticed that some of you still confuse multiplications. So for each of those pieces, we have to calculate scalar product between electric field vector and a surface vector. Surface vector is perpendicular to that piece, and its magnitude is equal to the area of that piece. And then we have to add products for all pieces constituting the surface. Now, how do we create currents flowing in substances? Well, if it is space, empty space, then in principle, if a particle starts moving, then it is going to move through the space. So we can have current through vacuum, without pushing charged particles. However, if we think about a substance and how current can flow in a substance, and actually in technology here on Earth, most of the time we are pushing charged particles through substances, and we make those substances in the shape of wires, so then we can steer how the charged particles flow. And in order to make them to flow, we have to do something with that substance. So let's say that we have a substance in the form of a wire, like this one, and in order to have current flowing in the wire, meaning the current flowing through a, well, we will see what do we mean by when we say current flowing in a wire. Now, in order to have current flowing in that wire, we have to push it. And what happens with the charged particles in such a wire is like with water in a river. Well, in most cases, that a steady flow is established in that substance. And if I consider various surfaces, like these 2 surfaces, current through this surface is going to be equal to current through that other surface. And the steady flow, charge gets not accumulated in that region over here between the 2 surfaces. And fact that it does not accumulate requires that whatever enters from one side, or whatever charge enters from one side, an equal amount of charge has to exit on the other side. Otherwise, we would have accumulation or depletion of the charge in that region. So, considering this analysis, we can conclude that current through every surface, every cross-sectional surface in the wire has the same value. And we assign this value to the current in the wire. So when we say that current 1 ampere flows in a wire, we mean that current of 1 ampere flows through every cross-section of this wire. Right? We don't have current in a point. We can have current density at a point, but current is always through a cross-section and through a surface, and therefore when we say about current in the wire, it means current through a cross-sectional surface of the wire. Well, now in order to force this current to flow in a substance, we have to push it. We have to create electric field inside that wire in order to make that current to flow. If you recall that simulation which I showed yesterday, it is that if we didn't have something pushing charged particles, the lattice of the substance will simply eventually stop it. It will be well, the electrons, let's say that it's a copper wire electrons in that copper wire will stuck like a St. Patrick's parade in woods. Yeah, if you are trying to run and eventually everybody hits a tree, and when you hit a tree, if nothing else pushes you, I mean, you push yourself, you propel yourself by asking the ground to push you forward after you hit the tree. So the same thing happens in a substance. If electron gets scattered on an atom, it has to be accelerated in the direction of the drift velocity. Otherwise, it would never move. This is not well, and the law which relates actually the current as the phenomenon with the external interaction is referred to as Ohm's law. And well, we have various versions of this Ohm's law. Now it's almost the most modern version, which relates current density at a particular location with electric field at the same location. And it says that current density is proportional to electric field vector. In general, the relationship, I mean, this proportionality coefficient doesn't have to be a number. For some substances, it can be a tensor quantity, which means that it will be a matrix rather than a simple number. In this case, current density doesn't have to be exactly in the same direction of electric field vector. So electric field vector could be, for example, that way, and current will not flow this way but that way, or this way. It was something similar. We have already, I mean, those of you who discussed, who took Physics 1 with me, you may recall that we had a tensor relationship between what and what? Stress and strain, correct. Relationship between stress and strain also didn't have to be proportional, so we had a tensor relationship. However, in our program, we assume that current density, I mean, because for most substances, we will have to look for exotic substances in order to have a tensor relationship. For most substances, like metals or copper, aluminum, and whatever we use for wires, current density and electric field vector are in the same direction. This proportionality coefficient is called conductivity of the conductor. Now let me remind what a conductor is. Conductor is a substance in which charged particles can move almost freely. Yeah, if they were moving freely, then we wouldn't have to push. But because they have almost freely, in other words, the substance itself tries to prevent the motion, then we need an external factor to make the charged particles to move. All right. Now we are at the point to understand a second device, electrical device, very common in electronic circuits. It is called a resistor. And similarly to this, how we described capacitor, I want to describe a resistor. So a resistor is an electrical element which also has two sides, and at any instant, current flowing to the resistor is supposed to be proportional to the potential difference across the resistor. Look at the difference between capacitor and resistor. In a resistor, current is proportional to the potential difference. In a capacitor, charge transferred between the plates is proportional, or charge stored on the capacitor is proportional to the potential difference. This is a symbol of a resistor on a circuit diagrams. It actually kind of reminds a wire, a wound wire, because we make resistors from wires. In a moment we will see how. And like in a capacitor, I want you to be precise about the relationship between current and potential difference. Like in case of capacitor, I wanted you to know which potential difference to relate to which charge. Here we have to be also consistent with this, which current to relate which potential difference. And all right, so if we mark current that way, I mean if we say that current, we are considering current flowing to the right. Now it doesn't even have to be conventional current, because I said that by conventional we say that current flows in the direction in which positive charge is being transferred. For a resistor, we don't care if this is the direction of positive charge or negative charge. It will work as long as you are consistent. So let's say that I'm considering current flowing, current to the right, which means that I imagine a cross section across the resistor, and I calculate charge moving from the left to the right, no matter if it is positive or negative. If it is positive, then the value of the current is going to be positive. If this charge is negative, so conventional current flows the other way, then the value will be negative. So potential difference, and if you mark current to the right, then you have to take potential difference between the point which corresponds to the tail of that arrow, and subtract potential at the side of the resistor which corresponds to the head of the arrow. This potential difference is proportional to the current which we marked. The proportionality coefficient is called the resistance of the resistor, and it is measured in ohms. And a 1 ohm resistor will be such a resistor that if potential difference across the resistor is 1 volt, then current flowing through the resistor is going to be 1 ampere, or vice versa. If current through the resistor is 1 ampere, potential difference is going to be 1 volt. If something like this happens in the resistor, then we say that the resistor has resistance of 1 ohm. Now, I want to warn you about some misconception. Because what does a resistor really do? Does it resist? What does it resist? Well, nothing. It doesn't resist anything. I mean, let's say, if we imagine that we have a battery, let's say that this battery produces 1.5 volts potential difference between this point and this point. We will talk about battery in the future, but this is what batteries do. Batteries produce potential difference between various points. So let's say that potential here now is 1.5 volts higher than on this side. What current is going to flow in the resistor, in the battery now? How much? There will be no current. I mean, it is that if current were flowing in batteries like that, they would not be able to keep them in the stores because they would get discharged on themselves. The currents don't flow in a battery until we connect the two ends of the battery through a circuit. So, for example, I can connect this end and this end with a circuit, and now the current is going to flow. So what has the resistor done? Has it resisted the current? Actually, it made the current possible. Current wouldn't flow without that resistor. Really, probably it would be more appropriate to call a resistor a conductor. Why don't we call resistor a conductor? Because resistors conduct current, not resist current. How come that we don't call them conductors? A wire, by the way, is a resistor. Every wire is a resistor. It's a resistor with small resistance. Ideal wire is a resistor whose resistance is 0. No, but well, the reason that we don't call resistors conductors because we have already used word conductor. Yeah, what is a conductor? A substance in which charged particles can move almost freely. We call those substances conductors. So now we cannot use, I mean, in principle we could, but we will introduce more confusion into physics that we already have. So because of that, we will call the device a resistor. How about now we exercise that relationship, and I want to show you that it does not matter how you connect these, how you mark it, as long as you are consistent, we will be fine. So, how about if we think about this circuit? Let's say now that this is an ideal battery. Well, if we take 1 kilo ohm resistor, that battery will behave like an ideal battery and will maintain potential difference between these 2 points to be 1.5 volts. Potential difference is 1.5 volts. So if I, let's say, call this V plus and this V minus, this difference is V plus minus V minus. So let's find current in this resistor. And consistently with that formula, I can write down that this is V plus minus V minus is equal to, which is 1.5 volts, is equal to the unknown current multiplied by 1 kilo ohm. And from this, I find that the current is going to be 1.5 milliamperes. What did I find? What is that 1.5 milliamperes? Current. Which current? Through the resistor. Okay. Now, which current through the resistor? Which current through the resistor is 1.5 milliamperes? Will Eric say it louder? No, it's through the resistor, but it's simultaneously through the battery, but we will talk about this later. But which one, besides, Mike said that it's through the resistor, so it cannot be, stick to the resistor. So this is current through the resistor, but I'm asking which current through the resistor. You don't see a problem that there are more than one possibilities, right? Andrew, can you see 2 possibilities?
Phenomena versus quantity?
No. Which one has 1.5 milliamperes? Phenomenon or the quantity? The quantity, correct. This is another story that we can confuse the quantity with the phenomenon. But even for the quantity, there is ambiguity. I don't know which current is 1.5 milliamperes in the resistor. What are my options? Well, is it this current or this current? Which one? Let's vote. So who votes that it's the top one? Who votes that it's the bottom one? You're right, it's the top one. The top current is 1.5 milliamperes. Let's find out the bottom one, okay? What will be the bottom one? How did you get it? Yeah, somebody already said that it is going to be negative 1.5 amperes, and it is true. But I want to find it out. Yeah, because indeed, this current says at what rate charge is being transferred in this direction. And, well, the positive, since electric field vector is in this direction, current density is also in this direction. So in this direction we have transfer of positive charge. Well, it's equivalent of transferring negative charge the other way. And in fact, current, if current in a circuit is carried by electrons, so really charged particles move that way, electrons move that way, from lower potential to higher potential. So negative charge is being transferred to the left. Let's change the current, the color. So this was 1. Now let's find out current 2. So if I multiply current 2 by resistance of the resistor, I should get potential difference across the resistor. But which one? It should be this potential, potential corresponding to the tail of the arrow. It's V minus, minus potential corresponding to the head of the arrow, V plus. Now this potential is potential V plus, consistently with this drawing, is higher than that one. So this value is minus 1.5 volts. So from here I find that current 2 is equal minus 1.5 milliamperes. As long as you are consistent, you are always to come to the same conclusion. So if I think about which way conventional current flows, no matter if I look at this value or at this value, I know which way conventional current flows. Conventional means that the one which is carried by positively charged particles. Conventional current flows to the right. But in calculations, very often you won't be able to say in advance, yeah, over here, I was able, and some of you were also able to determine that the current, that the conventional current is going to flow from higher potential to lower potential. But if you look at the circuit, very often you won't know where potential is higher. All right, let's see how a resistor is constructed. And we just have to take a, well, kind of thick wire of a substance, or a cylinder of a substance. So this is, and this will make a resistor. Imagine that this is a conductor, and we make a cylinder from the conductor and connect both ends of this conductor to wires and create potential difference across this cylinder. So what do I have to verify in order to determine if this is really a resistor? Do you remember what we had to verify? Oh, very good, Anna. We have to verify that potential difference across this device is proportional to current flowing through this device. All right. So let's relate current to potential difference. Now current, and actually I can assume I mean, if I produce potential difference, I mean, one potential on this side and another potential on this side, I can assume that current density is almost uniform. So let's say that I have consider a cross section, and for simplicity, I will take even cross section which is perpendicular to the current density inside of this device. And now current density is uniform across this entire surface. So current density, so current, I have to calculate flux of current density over the surface in order to get the current. And if current density is uniform, it's easy to find. It's easy to integrate the flux. What will be the value of the flux? First, we have to divide area into small pieces. For each piece, we have to calculate scalar product between current density and differential surface vector, which is also in the same direction. So what is the angle between current density and normal to the surface? 0, correct, 0 degrees. Cosine of 0 degrees is 1. So for that differential tiny piece, it will be magnitude of current density times the area of tiny piece times 1. And now we have to add over all pieces constituting that cross-sectional surface. I can pull out 1, or just ignore it, and magnitude of current density in front of the integral, and then I have to add areas of small pieces. What am I going to get? If I add all areas of all segments constituting that cross-sectional surface, what am I going to get? The area of that cross-section, correct. So current density, by definition, is flux of current. Current is by definition flux of current density, and it's easy to integrate. It will be magnitude of current density multiplied by cross-sectional area. Now, why did I do it? Why did I actually complicated quantity? Why I changed quantity from current to current density? Because on the previous slide, or 2 slides before, no, on the previous one, I had relationship between current density and electric field vector. It was 2 slides ago. So I can write down now that magnitude of current density is equal to conductivity of the substance which I used to make the resistor, multiplied by the strength of the electric field in that resistor. Now that one, on the other hand, depends on potential difference between these two. I look that these are like plates. So I can assume that electric field over here is almost uniform and related to potential difference. So electric field strength is equal to potential difference between this point and this point divided by the distance from this point to this point. It's almost like in a capacitor. What should I do next? Adam. It was your idea to do whatever we did. And let me remind you, Adam wanted to relate current flowing in the device with potential difference between its ends. If we get it that there is a proportionality between these two quantities, it means that the device is resistor. Yes, Robert? Robert is happy, and we all should be happy now. We got it. Current flowing in that resistor is proportional to the potential difference across the resistor. I mean, this device, which means that this device is a resistor. Now, we can now even find out what is the resistance of the resistor. How properties, I mean geometrical properties and material we choose affect the resistor. Yeah, because this coefficient over here is an inverse of resistance, right? Because potential difference across the resistor should be equal current multiplied by resistance. I have to move this factor to the right hand side and get the value for resistance, and I can write it down that way. That resistance of a resistor depends on the choice of material. It depends what is the conductivity of material. It's proportional to the length of the resistor. It's the distance from one side of the resistor to the other side of the resistor, and inversely proportional to the area of the cross-sectional area of the resistor. It is not convenient to have this inverse over here, so sometimes we refer to inverse of conductivity as resistivity. Well, we always do that, actually. By definition, resistivity of the substance is inverse of conductivity of the substance. Each substance has simultaneously conductivity and resistivity, and in some books or some tables you can have resistivity, in some tables you can have conductivity. You have to know that if you know just one, it's enough to design a resistor. So now, look what a wire. Yes, Robert has a question. Never mind. Okay. Now, when we want to make a wire, I said that a wire is a resistor. And what a wire is supposed to do? A wire is supposed to work in such a way that potential difference between this point and this point is 0, and the current still flows. This is what we want from a wire. We want make wires in such a way. It's impossible. All wires actually, there's no wire, only superconductive wires will have this property. All wires in your TV sets and all other iPods and so on, in all other electronic devices won't have this property. They will always produce potential difference across the wires. There will be always potential differences across the wires, but ideally a wire will be such that current can flow through that wire and there is no potential difference across it. What should be conductivity of the substance from which we will use for wires? And resistivity as well. And we should have that potential difference should be 0 and the current not. Now, what should be conductivity to get such a property? Now, cross-section area of a resistor of a wire is a fixed number, length of the wire is a fixed number. What should be conductivity to get current flowing with 0 resistance? Now let's say that we want to have 1 milliampere in a wire. So now something times a certain constant, area over length, and here we have 0 volts. How to make it possible? I mean, we can actually, we won't be able to find, well, I don't know, it depends how you look at that value. But how to prevent contradiction? Yeah, can conductivity be 10 or million? Well, it has to be infinite. Conductivity of the substance has to be infinite. How about resistivity? Let's take a look at the resistivity. What should be resistivity of a wire? of the material which we use for the wire. 0. So this way we will have that potential difference is equal, which we wanted to be 0 volts, is going to be, well, resistance is equal to resistivity times length of the wire divided by the cross-sectional area, and we wanted to have it at 1 milliampere. Yeah, these are finite numbers, so in order to satisfy this equation, resistivity has to be 0. And indeed, this is how we make wires. We choose substances like copper, aluminum, because they have very high value of conductivity and at the same time very low value of resistivity. Now, if I want to make a 1 kilo ohm resistor, which is a reasonable value for a resistor used in electronics, I wouldn't take copper. Why? I could, in principle. I could use copper and make 1 kilo ohm resistor, but I wouldn't. And nobody who is not insane would not use copper to make a 1 kilo ohm resistor. Why not? It would take a lot of copper. Yeah, in order to have resistance of 1 kilo ohm, let's say that we take a wire which is, we should take a wire which is thick or thin in order to have 1 kilo ohm resistor, which is relatively high resistance. A what? Thin. Now we want to make area as small as possible, and because then we could use shorter. If we make large cross-sectional area, the wire would have to be longer. Yeah, think about it. That let's say that I want to double resistance of a wire by changing area. I want to double it. What do I have to do with the area? Yeah, I'm talking about copper. Yeah, so copper, we will have a particular resistivity. So we won't change resistivity. The only thing which I want to change is area, and I want to double resistance of this resistor. What do I have to do with the area? Shrink. I have to make area 2 times smaller. It will double resistance. So now what do I have, let's say, what do I have to do with the length if I want to double resistance without changing the area? I will have to double length, correct. So in order to save substance or to save copper, if I want to use it for 1 kilo ohm resistor, I would like to make as thin wire as possible, because then I can make it shorter, and if I make it shorter and with a smaller diameter, I will use less copper, so it will be cheaper. Yeah, because we have to think about the cost, among others. Not mentioning that if I wanted really to use a 1 millimeter a wire with cross-sectional surface area 1 square millimeter, I will have to take a lot of very long copper. Can you imagine now putting it into your iPod? I mean, the copper itself will weigh a few kilograms. Will be very heavy resistor. All right, so for resistors we should choose substances with what type of conductivity or resistivity? So resistivity of those substances should be high, correct, and conductivity of those substances should be low. All right, now conductivity and resistivity of substances is a function of external parameters, and one of the parameters which affects it most is the temperature. in general, actually, I mean, we live in a very narrow range of temperatures, so for a lot of quantities, we can approximate dependencies with a linear function. And, well, for resistivity, we can write down that resistivity at an arbitrary temperature is equal to resistivity at a particular temperature. And for this particular temperature, we choose usually room temperature. So this is resistivity at room temperature. And then we have a term which says that the resistivity is a linear function of temperature. T0 is that room temperature. This coefficient is called temperature coefficient of resistivity. And if I look at how various substances behave, metals have such a property that if we increase temperature, resistivity of the metal is also increasing. However, this is not true for every substance. Semiconductors, for example, have the other property. It is that they are, when we increase temperature, their resistivity decreases as well. All right, so I have a puzzle now. A regular incandescent light bulb uses tungsten wire. I mean, we use tungsten wire to make light bulbs, and we run current through that wire. And when we run current, it becomes hot, so hot that it starts to emit light. Resistance of the light bulb is higher when the light bulb is on or off. Who votes that resistance is higher when the light is off? Who thinks that resistance is higher when the light is on? Actually, there is higher support for the light on, and this is correct answer, and it's not because of democracy. It simply, tungsten is a metal. So at lower temperature, its resistivity is lower than at high temperature. Therefore, when that wire is cold, resistance is also lower than when we turn it on. Which means actually that if I apply, when I'm switching the light bulb on, the initial current has a higher value or lower value than when it is at the normal operation. So who votes that initially current has a higher value? Who votes that it has lower value? Those of you who voted that it's higher, you were right. When we turn on the light bulb, the current in the light bulb is higher, and it decreases until the temperature stabilizes to the operational value. How about if we talk about the connections next time? I don't want to rush through this subject, so we will end the lecture at this point.